huh? Okay. So let's see how we define sets within operations. Okay. So if we write set in a slightly different way, say x is in S. Okay. And so what does a set notation like this actually mean? What this actually means is the set of all x in S, and that symbol means such that let's have okay, so in the last video, we were talking about subsets, okay? And so how would you define a subset without just giving it a name, okay? Well, you would take a larger set, say S, okay? We say, all right, for all x and S, this set that we're talking about right now, it just has to be the x within S such that this, whatever condition we give it, P of x is satisfied, okay? This is what this type of notation means. So let's look at a couple of them. A couple people saw right now. Wait a second. Okay. So let's look at some of the sets we were talking about just a minute ago. Let's say x in z, meaning x is in the integers, any x which is an integer, such that -3 is less than x, which is going to be less than 4. Okay. So this set right here is, all right, the set of all x and x. So this is the set of all integers, all portions of this set, such that they satisfy, that's what's meant by P of x, this inequality. Okay? So if we were going to write this in set notation, well, it already is technically, this would be -2, -1, 0, 1, 2, and 3. So that is the set of all integers such that they satisfy this inequality right here. Okay, so that's kind of translating it into our normal language. In mathematics, we have a very large tendency to use a lot of symbols, and so we'll get into a lot of different symbols that try to express these things. Okay, so let's change this set just a little bit. Okay, so let's change this set by altering S. So if I write x is in the positive integers existing between -3, which is less than x, which is less than 4. I'm kind of bumping into myself a little bit there, but. Okay, so does anybody have a guess? What would be x and z plus only the positive integers, not including 0? Yes? 1, 2, 3, yes, thank you. That's it. It's just positive integers. And we can also include this type of set notation where we can include functions as well. So let's say let's make it a little bit more complicated. Let's say x is going to be any integers, and then such that x plus 3 exists in the positive integers. Okay, so any integer, all right, what is this problem saying? This is saying x is in z, so x is any integer. But x plus 3 has to end up being a positive integer, not including 0. So, let's say from the left, where do y'all think we would start?
3, 4.
Well, 4 plus 3 would be 7. That's positive. But what's 0 plus 3? Still 3. Yeah. It would actually start at -2. So where would be the cutoff? If we plugged -3 into this, we would get -3 plus 3, which would be 0, which is 0 is not considered a positive integer, it's 0. So this step would actually begin at -2, -1, 0, 1, 2, 3, and then all the way off to infinity. These are all numbers that if you added 3 to them, all integers, that if you added 3 to them, you would end up with a positive integer. Okay? Oh, and there's one other set that I have to mention. Yes?
So can you explain how you know it starts at -2?
Okay. So the question was, how would I know that this starts at -2? Well, the first thing that I would say is, all right, if I'm talking about integers, and I know it has to be a positive integer. So the question I would ask myself is, well, when would this be 0? For what integer value would give me 0 for this? And so if I plugged in -3 into this, I would get -3 plus 3, which is 0. Okay? And then I have to ask myself the question of, well, what's the next integer over to the right? Well, if I plug in -2 into this, well, -2 plus 3 would just be +1, which would give me the first positive integer. And then -1 plus 3 would be 2, and that would be the next positive integer, and you can see that it goes from there, that it just keeps giving me positive numbers when we add 3 to it. So I guess if you want to think of another way to put this, if you said x plus 3 has to be greater than 0, okay? That would mean that x has to be greater than -3, okay? And so x has to be an integer which is greater than -3, so that's why we begin at -2. Well, within this one video, I want to mention one other thing. There's actually a set that comes up important later on before I get into Cartesian products and ordered pairs. Well, let's see how I wanted to phrase it. Oh, no, I don't want to phrase it like that because that implies an element. There is something known as the empty set, and this is just a set that does not contain any element. And then there are some logical arguments of the empty set is, I don't want to get into it, arguing whether it's a subset of other things. But yeah, we can get into that too. I'll stop.